I'm going to show you some more examples of how to use implicit differentiation. So our objectives are the same as last time. We're going to focus more on recognizing functions that should be differentiated implicitly. We're going to find a lot of those derivatives. What I want you to know is, great, you know how to use implicit differentiation. But if you don't understand why that stuff works, you might have trouble on the AP test. So go back and watch the theory video if you haven't already seen it. All right, so when I give my students in class this lecture, I like to hand them this equation because it looks ugly and scary. So if you want to, you can participate in this. Most people can't recognize what this shape is. So try to find some ordered pairs by guessing and checking and try to graph. If you don't want to do that, I'm about to show you the graph of x squared plus y squared minus 2x plus 3y plus xy equal to 0. Even with that x squared, y squared terms, we don't end up with a circle, we actually end up with a rotated ellipse. Now, that's a nice smooth curve everywhere, so it's going to have a derivative almost everywhere. Not quite everywhere. Down here, a tangent line would be vertical. Over here, a tangent line would be vertical. So aside from those two spots, this derivative would exist everywhere. Okay? Now, this is a great function. Oh, shoot, not a function. This is a great equation to do implicit differentiation with because it has x and y terms. But let's think about this. Could someone, maybe it's you, maybe it's not you, rearrange this whole thing, y equals only x's over here? Maybe you could, maybe you couldn't, but hopefully you can imagine that. If you could take the derivative of that, we would call it dy dx, and that's actually what we're looking for. Do you want to solve for y? I don't either. So this is a great time to use implicit differentiation. So we're taking the derivative of this whole thing with respect to x, means we're treating x as the input variable. So the derivative of x squared is 2x like always. What's the derivative of y squared? Well, 2y at first, but remember, y is that x junk stuff that we didn't want to solve for. So that's some function. And right here, we have that function squared. So this is chain rule. So the derivative of y squared is 2 times that y function times the derivative of that y function. So what's the derivative of negative 2x? That's easy. A negative 2. What's the derivative of 3y? Well, that might be easier to explain. So the derivative of 3y, or 3 times all that junk, would be 3 dy dx. Okay, x times y is a product of two functions. And the derivative of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first. The derivative of 0 is always 0. Doesn't matter with what we're doing a derivative perspective. Let's see. We knew what our answer was going to look like. That was dy dx, but we have 3 of them. So I'm going to get rid of everything that's not a dy dx. So 2y dy dx stays. And I'll subtract 2x to the right-hand side of the equal sign. Negative 2 doesn't get to stay. It gets added to the right-hand side. So plus 3 dy dx stays, plus x dy dx. And, well, we're going to have to subtract y over here. How do you get all those dy dx's together? Someone is yelling at the screen, factor. That is correct. And the right-hand side is still negative 2x plus 2 minus y. And then to get dy dx by itself, we just divide. Now it shouldn't be shocking that this derivative has both y's and x's in it. That's actually a good thing, because now if you have an ordered pair and you need to find the slope of the ellipse at that ordered pair, you just plug in the ordered pair. Why is that a good thing? Well, if you only know x is 2, or maybe only know x is 4, 2 is not a great example. If you only know x is 4 and you don't exactly know the correct shape, you don't know which slope is correct. Okay? However, if we know the ordered pair, like 4, negative 1.5, something like that, or 4, negative 5.5, whatever that is, those ordered pairs would give different slopes, and that's almost like a function. Well, it is a function, but usually we like functions to have just one input variable. Okay, what shape is y squared equals x? That's a parabola with its vertex at 0, 0 and opening to the right. And this is another great time to use implicit differentiation. We can all solve for y. That's very easy. But you end up with two things. Y is the square root of x and y is the negative square root of x. Which means if you're going to do a derivative, you have to do a derivative of each of those pieces and then keep track of which one to use and when. So, y squared is actually that thing that I just erased. Being squared. What's the derivative of something squared? It's 2 times that something. What was being squared? Some function named y. And that function would have a derivative dy dx. What's the derivative of x? With respect to x, just 1. And so dy dx is equal to 1 over 2y. And that might be a little weird as well, because you're thinking, well, shouldn't that have x's in it? Well, maybe, maybe not. This is kind of nice. So instead of choosing an x to put in to find the slope of the tangent line to this parabola, we can just put in a y. And so let's put in negative 1 for y. How about using y equals negative 1? That would be dy dx is equal to negative 1/2. Does that seem like a good slope? Well, maybe if I had drawn better, but at least the sign is negative. Let's use y equals positive 1. That would be dy dx is equal to positive 1/2. And we know about the symmetry of parabolas, so that seems logical. Well, I hope it does. Now, up until now, you should have only been using the power rule for negative exponents and for positive exponents if those exponents were integers. Okay? However, now that you know implicit differentiation, we can show that the power rule works for, as long as you have a variable base like x, you can use any exponent you want. Okay? So, shoot, I thought I had a blank screen next. This might work a little bit easier if first we do the derivative of, I don't know, let's say to the power 2/3. So let's pretend instead of y is x to some number a over some number b, x to the power 2/3. So y is equal to x to the power 2/3. Now I said that the power rule is going to work, but we should be using things we already know to prove things we don't know. So I know that the power rule works for x squared or x cubed or things like that. So can I get rid of either the 2 or the 3? Well, let's get rid of the 3. Okay, so how do I get rid of that 3 in the exponent? That's really a cube root. So we could cube this side, and that would give x squared. I can definitely do the derivative of x squared. And if I cube the right-hand side of an equation, I'll cube the left-hand side of an equation, y cubed. So we couldn't have been able to do this before the implicit differentiation stuff. Now we can. Well, let's start on the right-hand side. The right-hand side is easy. The derivative of x squared with respect to x is 2x, nothing else. The derivative of a function like y cubed is 3 times that function squared. Our function is y, which has a derivative of y prime. Okay, so let's solve for y prime. Y prime is equal to 2x over 3y squared. That doesn't look right. Let's go back to what y was equal to. Now it's hard to see what y was equal to. What was y equal to? Y was equal to x to the 2/3 power. So 2x over 3 times x to the 2/3 squared. And oh my gosh, what is that? Let's think about this. So the numerator is x to the 1st power, and the denominator is x to the 4/3 power. So this is 2 over 3 x to the 1/3 power. Oh, can't really write that 3. Okay, just pretend that's in the denominator. Did that work? Sure, let's rewrite y prime. That is 2/3 x to the power negative 1/3. I don't know if that proves anything to you, but let's confirm a little. Y is equal to, we started out with x to the 2/3 power, and if we use the power rule, what would we do? We'd say y prime is 2/3 and then x to the power 2/3 minus 1 or negative 1/3. Okay, those match up. But I guess all we proved was that the power rule works for x to the 2/3 power. We need to prove for any exponent written as a ratio of integers a over b. So we kind of need to do all that work again. But I've decided I'm going to do that in another video. That should be separate. This is super friggin' weird. Okay, so y is sine of xy. And weirdly enough, both of those y's mean the same thing. They're both some function y, but one is y equals and the other is inside. So really, there's no way to get those two y's together. You might be thinking, well, what if I take inverse sine of both sides? Great, go for it. You'll get inverse sine of y is xy. So now the y on the left is locked up, while the y on the right is free. That's really your only option, which means if we're going to find the derivative of y equals sine of xy, we need to use implicit differentiation. So the derivative of y is just dy dx. The derivative of sine of something is cosine of something. So we're actually using a chain rule twice here. Here's the first version. Cosine of xy times the derivative of xy. And the derivative of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first. Okay, you should have expected your derivative to be dy dx is equal to, so we're going to have to do some algebra. Dy dx on the left, and I have to distribute. So that's going to be x cosine xy times dy dx plus y cosine of xy. And so I probably shouldn't skip over what I'm doing in my head. So dy dx minus x cosine xy dy dx is equal to y cosine of xy. Factor out the dy dx on the left and divide by 1 minus cosine of xy. I know I said I wasn't going to skip steps, but I also can't really go on to the next page with you folks seeing everything on this page at the same time. So another great time to use implicit differentiation because we really can't solve for y. This is not implicit differentiation, but bonus, you might see this in a warm-up. This you should be able to do in your head. Limit as h goes to 0 of cosine of pi thirds plus h minus cosine of pi thirds over h. You should realize there's a missing pi thirds plus h minus pi thirds. This is the derivative of cosine of x at pi thirds. Cosine of x has a derivative of negative sine of x, but we're evaluating at pi thirds, which hopefully you can do in your head, and that's negative root 3 over 2 because of the negative out front. Careful here. What I mean by that is, if you're in the habit of writing the easiest thing, you'd write y prime, you have to use dy dx. Is this a good reason, a good time to use implicit differentiation? Absolutely. I really don't want to solve for those y's, and I'm not even sure I can. But with implicit differentiation, I don't have to. Okay? So we just go through and take the derivative of this thing term by term, and then we'll have to solve for dy dx, but I'm probably going to pause there because I don't feel like doing the algebra. I'll leave that to you. The derivative of x cubed is 3x squared, or at least the derivative of x cubed with respect to x. And, let's see. I guess negative 3x squared y is a product of two functions. I'm going to put the negative out front just so I don't make a mistake. So the derivative of a product of two functions, and I'm going to think of this as 3x squared multiplied by y, is the first function times the derivative of the second function. Of course, the derivative of y is dy dx, plus the second function, which is y, times the derivative of the first function. Let's see, 6x. Okay, now we move on, and yay, another product rule. So I'll again group 4x and then y squared. You could actually put the 4 out front of the brackets and distribute later. I'm not going to. The derivative of a product of two functions is the first function times the derivative of the second function. Ooh, chain rule here. The derivative of something squared is 2 times that something times the derivative of that input. Okay, don't forget, we're doing a product rule. So that was first function 4x times the derivative of the second function plus the second function times the derivative of the first. Make that more multiplying, Mr. Scholl. Bracket. And the derivative of 12, any constant, has a derivative of 0. And maybe I'll finish this one up and then stop. So we're going to have to distribute and be careful. So 3x squared minus 3x squared dy dx. We can't combine those because of the dy dx. Minus 6xy plus, what is that? 8xy dy dx. And then distribute 4x, and the last, I said the derivative of a constant is 0. Thank you for yelling. I actually heard you that time. Let's see, do I distribute? No, that 4x is only in here, so this is just plus 4y squared equal to 0. We're almost there. We're going to do two things on the next line. We're going to group together the terms including a dy dx, and we're going to move everything else to the opposite side of the equal sign. So dy dx is equal to, I'm going to use the positive one first, that's just prettier, 8xy minus 3x squared, only terms with dy dx. And again, I'm going to try to make things look pretty, so I'll start with negative 6xy added to the right side becomes positive 6xy, minus 3x squared, minus 4y squared, and then we have to solve for dy dx, which is everything we used to have on the right-hand side of the equal sign, divided by 8xy minus 3x squared. Ooh, that was a lot. I'm going to pause there. I'm sure you can find additional implicit differentiation practice online. Good luck.